Hello, I will be presenting iiANET Inception-Inspired Attention Hybrid Network for efficient long-range dependencies. This is a submission to TMLR. My name is Yunusa, and I'm from NewraLab, Suzhou, China. So we would start with the agenda for today for our presentation, which is we're going to state the problem, and we're also going to state the challenges. And we're going to look into previous works that has been done in terms of capturing long-range dependencies, and also try to find the gap. And we're going to present what we actually do for our solutions, and we're going to present the results, and we're going to also compare our results with the previous designs. And in the end, we're going to conclude. So I would like to start with defining what is actually long-range dependencies, especially in images. So it's a situation whereby you have an object that expands the whole width of the image. For instance, you can see the image on your left-hand side, which is a cat. And let me try to use my pen. So you can see this object. It's a little small object within a bigger frame of the cat. And you can see it didn't extend the whole width of the image. And we can classify this as a short range. And on your right-hand side, which is an image B, it has a long-range dependence. So you can see the image of a growling cat, which extends the whole of the image. So you can see the objects. So CNNs actually, which is convolutional neural networks, find it challenging to capture the relationship when the object extends the full width of an image. For instance, this B. So there is actually a lot of tricks that we can actually deploy to improve or enhance the capturing of long-range dependencies. One of them is to use dilation. So you can see here, this is dilation. You can see the receptive field has been expanded here. So now we can actually capture the relationship, the wider relationship between the image and without using much resources. So then we have VIT, which is vision transformers. So these are very excellent models that are very good with capturing long-range dependencies, but they have one problem, which is complexity. So they are very wasteful in terms of resource usage. And this has to do with the way they have been structured, and because they look into all the whole tokens in an image. And so with this kind of approach, it's going to be very difficult for we to have an efficient model which is going to capture long-range dependencies. So we have a dilemma, which we have CNNs, which are very good in capturing short range, but not good with capturing long range. But they are very good with especially feature extractions. And we have also dilated convolutions, which are kind of like a solution to what we actually want with capturing long-range dependencies. But they have a problem of artifact. So they have because we can see there is a dot, there is a space in between each kernel. So this, in the end, it results to mostly a artifact. So here we have also VIT, which are very excellent in terms of capturing long-range dependencies, but the problem with them is the complexity. So the complexity is quadratic, as you can see here. Yeah, with with yeah, so the complexity is quadratic with sequence length. Yeah, I forgot the term to use. So also on the right-hand side, you can see an example of why we actually need a model that can capture long-range dependencies. So you can see this image as an input, and you can see it's a viaduct, which is a road network, and you can see it extends the full the full width of the image. So, sorry. So in this kind of scenario, we will be requiring a model which is good in capturing long-range dependency. So you can see here the resulting ResNet. You can see it captures some relationships here, kind of like locally. So this is what actually it sees, and it's a receptive field. And here too, you can see all the small like heat maps. So this is what it's kind of like capturing. And here you can see VIT. So VIT actually has a problem of interpretability. And this is why you didn't see the way it captures the long-range dependencies. And this is actually due to high norms. And in the last example here, we can see iiANET, which is our solution. And you can see it's kind of like improves the capturing of long-range dependency. So you can see it's extends the object in the image. And also here you can see this road. It kind of like goes along like a long range. So we have a dilemma, which is we want to design an object. Sorry, we want to design a model that can capture long range dependencies, and we want to do it efficiently. So this is where the dilemma is. So we move to the next. Oops. So this is what actually has been done previously. And we can see there has been several methods to hybridize, to like combine CNNs with attention mechanisms, or we can say with transformers. So one of the methods is to use a serial hybrid. So in serial hybrid, as you can see with coordinate, let me on my pen. So as you can see with coordinate here, you have CNN, then the output of your CNN is the input of your VIT. So just like it says like serial, so it kind of like combine it along a serial route. So here you can see there's a depthwise here CNN block, then it now combines, this is a skip connection, it now combines it with VIT. So it does this repeatedly. It repeats this like 3 times. And we have a problem with this kind of approach. It's just trying to combine VIT with CNN, which in theory, I think this is going to increase the complexity. So this is something that we don't want. So we want to be able to come up with a design that is going to be efficient and also can capture long-range dependencies. So here you can see it has 168 million parameters, and here is the flops, and here is the accuracy, which is on ImageNet top 1. So here too we can see the hierarchical hybrid, and which is on CVT. So here you can also see it has a very high trainable parameters, and here we can also see it has a very high G-flops, and as well it has a very high top 1K accuracy on ImageNet. So actually what we actually want to do is to come up with a design that is going to be less resourceful, especially recently that there's a lot of issues with energy, and yeah, so we move to parallel hybrid also, which is kind of like the CNNs have a an input, a pipeline, so an independent pipeline, and the VIT also has an independent pipeline. So they both process the input independently, and here is where they actually kind of like fuse the two features, whereby the CNN processes the local details, and the VIT can process the global details. Also here, I think there's going to be a problem with also the way they're going to use the resources. As you can see here, this conformer B has 83 million trainable parameters, and also 23 G flops, and also the accuracy is pretty high. So our goal actually is to design an efficient hybrid CNN based model that is able to capture long-range dependencies. We would want to capture these long-range dependencies from the earliest layer of the network. As you can see in serial hybrid here, they capture most of the times the CNNs. The CNN capture the local details in the earlier network, and in the deeper network, it captures the VIT. So yeah, so let's go and you see our solution. Let me switch up this pointer. So yeah, so this is iiANET architectural design. And as you can see, we want to have simplicity. So I don't know, I can see I messed up with the, what is it called? With the pen, yeah. So we came up with an idea, and this idea was inspired from Inception networks, whereby you arrange different components or different blocks. For instance, in our case, we arranged a depth atros block, which is a dilated convolution, and we also added inverted bottlenecks, and we also added a multi-head self-attention. So we now combine these three blocks into one, and after combining them, we now shuffle, and kind of like using the way ShuffleNet used to shuffle these feature maps. And the output, then we output it. But before we even output it, we make use of iiANET, which is going to recalibrate these features for us. So here is our, we did modify the multi-head self-attention. As we earlier said that vision transformers have problem with interpretability. So we added registers to our attention. And this is exactly where we added the registers here. As you can see, I'm cycling it. And also here too, we added the registers here. So, and in the end, we discard these registers, and our network kind of like improves the interpretability. Yeah, so we added positional embeddings also. Let me switch on my pen. And we added the positional embedding into the dimension with height, I mean, and also width here. And yeah, then we added everything together, and we processed our multi-head self-attention, which we named r-MHSA. So I will try to re-summarize our architecture. So we came up with an idea which was inspired by Inception network, which is to arrange different components, and we arrange multi-head self-attention, and we arrange depth-wise convolutions, and also we arrange Arthur's bottleneck. So why do we arrange these stuffs in parallel? One of the reasons is for capturing multi-head self-attention is for capturing global dependencies, which will be able to capture the long-range dependencies. And also this inverted bottleneck is going to capture the local details, which is the short range. And also the Astros is going to capture mid-range. And here you can see we have different ratios. This one has 1 ratio, and this one has 6 ratios, and this one has 1 ratio. So why do we select this? After a lot of empirical studies, we came up with this as the best combination for design. Yeah. So we move to the next slide. Oops, I think my system is having. Okay, so I would like to recap and show us more details of how all these networks work, how iiANET works. So just like a normal CNN, which has an input here, and it has a stem, a layer, and it has the first block is being strided into 4, which is kind of like to shrink the feature map, the size of the feature maps. And it goes like that until you reach 32. So, and you can see the number of blocks times 2, times 3, times 5, times 2. And this follows the Inception network use of this number of blocks. And in the end, we have an average Boolean and a full FC. Yeah. So here is our input, and our input comes with X, and this X is divided into 3, X1, X2, X3. So each of these X's goes directly into either of these 3 components. And the first component is Arthur's block, and this captures the mid-range dependencies. And we also have the inverted bottleneck, which captures the local details here. And oops. And we also have the global multi-head self-attention, which helps in capturing global details and also long-range dependencies. So here are how we came up with our registers. So I would like, after the Q query and keys, the transpose, we added the registers, which has the same shape with the query key. And also here we added the value, which also has the same shape. And this is our last formula with the softmax. And this is the computational complexity of multi-head self-attention, that we came up, we modified. And as you can see, there is no much increment. And here is the addition. So it's very, very negligible. Yeah, where n is less than m. Yeah. So here is the and m such that it's width and height. So we move to the next slide. So for our experiment, I think I don't know how to remove these red marks. I think we just have to go with it. I'm sorry for this. Yeah. Oops, let me try to rearrange this back. Okay. So here is our experimental data set. We selected aerial image data set, which contains 10,000 images with 30 scenes. So why do we select this area data set? It's because it's prevalent with long-range dependencies. These are area images that have a lot of complex objects in them, like viaduct, like roads, like airport. So they don't mostly contain local details in them. Also, we made use of Oxford 3, and we also made use of for generalization. We made use of COCO and ImageNet 1K and also ADET 20K. for semantic segmentation. So this is our experimental setup, and training were done 90 or 150, and the batches were 16. We use Adam W as our optimizer, and the learning rate we started with 0.0001 with a decay of 0.05. Yep. And for fair comparison, some of these models that we compared with our model didn't have a result for some of in aerial image data set. So we made use of their original settings for fair comparison. And yeah, so here is our result. And for ImageNet 1K, we would just do the analysis, which is summarize analysis, which is iiANET L. That is a larger variant of iiANET, achieves a almost same result with coiANET, which is a serial hybrid of combining CNN and VIT in order to achieve a long-range dependencies in images. So here is our comparison. You can see we did it with almost 60% fewer flops, and also fewer, 3 times fewer parameters. So here is our result, 84.9, and our coiANET has 84.5. And this result actually are almost same, but ours with very less complexity. Yeah. So, and with aerial image dataset, iiANET also achieves a better accuracy, and while remaining compute efficient and relative to coiANET and also VIT. And also in Oxford, it shows also good generalization, outperforming ResNet 101. So we would move to detection and also segmentation. So in our segmentation, the first experiment that we performed, we made use of YOLO V8. So YOLO V8 as our detection pipeline. And for the backbone, we made use of iiANET B here and iiANET L, and you can see it achieves a higher AP bounding box on COCO, which is 64, and also on COCO instance segmentation. iiANET also achieves a very competitive performance, and also on the semantic segmentation, we made use of OpenNet, and you can see also iiANET achieves a competitive performance in both experiments. Yeah. So we would want to visualize whether to we actually evaluated our model, and one of the ways that we came up with this experiment is to visualize long-range spatial transport. So we came up with an object in the extreme left corner of an image, and this is our source. So we also came up with a target. Let me use my pen. So this is an object, and this is the target. Okay, so this object is going to be transported here, which is actually a very long range problem. Okay, and you can see how ResNet performs here, and you can see how iiANET also performs here, and you can see the convergence plot after 50 epochs, and you can also see the convergence of iiANET after 50 epochs. So you can see ResNet has almost like a straight line, not a straight line, but the convergence is not very good. And here too, you can see we did the similar experiment here and also here. We use a different shape of an object, and you can see the after 50 epochs, you can see ResNet is still struggling to kind of like converge, and you can see iiANET could converge a little far way better. And we did also with a square box and square boxes here, and you can also see here and also here too with different shapes, playing with it. Yeah. So we use same settings for this experiment. We use Adam W. We use 0.001 as learning rate, and we use 50 epochs and 224 and MS loss. So it's kind of like image reconstruction, and which is going to be transported from one corner to the other. Yeah. So I think we also did some grad camps, trying to compare our network with other networks. So we compared it with ResNet, EfficientNet, and CoordNet here. And we also compared with VIT, with botnet, and with iiANET. So based on our result, it shows that iiANET achieves a competitive result. And also here we used also Oxford dataset, and you can see iiANET extends the full width of the object of interest here. Yeah. And also you can see CoordNet also extends this object of interest, which I think it's because it's a combination of CNN and also VIT, which are very good in capturing long-range dependencies. Here you can see ResNet, you can see the CNN base, how they kind of like just capture the face of the dog. It's because of they cannot like extend, they cannot capture long-range dependencies. Yeah. So we also did some qualitative. I think my screen is messed up with this with this ink. I will just have to like continue. Yeah. Sorry for this. So yeah, we did on object detection, and this is FastR CNN Coco 17, and you can see our model also performs very good, and we also did some visualization using iiANET as the backbone, and you can see the result also looks pretty good. And we also use OpenNet for semantic segmentation, and you can see we use OpenNet. And also iiANET here performs really good. And yeah, so we performed several ablations, and one of the ablations is for scaling different component, and sorry. So what we actually did here was, I'm playing around with my, so what we actually did here in the first experiment is to like scale the channels of this iiABlock to see how it's going to like perform in terms of complexity, how it's going to increase. And we compared it with a pure multi-head self-attention. And as you can see here, the input is 112, and the out is either 32 or 64, and here 32 or 64. So in comparison, you can see the flops here didn't really drop much, and here also drops more in terms of the parameters, trainable parameters, and you can see the latency. It's iiABlock, it's faster in terms of latency, and this is also for throughput by image, and ours has a higher throughput. And we used 1111 head for each of these experiments. And we also did scaling for attention head. And oops, I need to pause this tutorial. Yeah, so sorry for my, I had to like plug in my power to my laptop. Yeah, so we continue. And yeah, oops, we're not on the same page. Yeah, so next is scaling attention heads, and we try to scale the attention head because in iiABlock, we also made use of some attention head, which is the multi-head self-attention. And we try to scale here. We try to use 2, And you can, when you compare the G-flops, when we use 2 here with also multi-head self-attention, you can see ours is 108 and this one is 112. And the latency also, it's better than multi-head. And also here too, the throughput is also better than multi-head self-attention. Yeah, so also scaling spatial dimension. So we played around with the spatial dimension. We started with 28 by 28, and you can also see multi-head self-attention, 28 by 28. And we put in 512 as the input channels, and the output channels is 1024. And you can see the flops here is 1. And here you can see the flops, it's a bit high. And I think this is because of the quadratic explosion of multi-head self-attention. So here, because iiABlock has several components, so it's going to like cushion this effect based on we combine several components for iiABlock. And the fusion that we did for iiABlock also, it's kind of like a very cheap fusion, which is just to concatenate and do shuffle. So I think this is why we have this effect on iiABlock. So for our ablations, all ablation experiment were conducted on aerial image dataset and using NVIDIA GeForce 2070 and CUDA 12.1, then PyTorch chip. So we continue also with the ablation, and we also tried the effect of different iiABlock variant on the aerial image dataset. So we played around different components. We made use of just purely all the blocks to be MBVCOM, which is the inverted bottleneck. And also here, we also use the inverted bottlenecks here and dilated. So you can see the result, how it goes up and down. And this is the best, or this is the optimal combination when we combine the 3 components together, and we achieved 80.57 top 1 accuracy. And we also did ablation on the effect of adding registers. And I think as we continue to add the registers, we continue to have an increase in the top 1, but the increase is very, very small. So yeah, so it didn't like really change much. And yeah. So we also did ablation studies on the fusion. So we tried different fusion methods, and we used cross-attention fusion. And as you can see, the parameters increased when we used cross-attention. And we also use a gated fusion. And here too, you can see we have an increment in the learning parameters, but we used additive fusion, which is just to concatenate and reshuffle them, just like ShuffleNet. Yeah. So we can see also here with flops, ours drop. Also lesser flops, also the latency is less. And the throughput is also higher, which is good per image. And you can see the difference actually is not much in terms of the top 1, although our network didn't perform better in this aspect. But the trade-off, this is what we're really concerned with, because we want to have a design that is very, very efficient. And you can see the trade-off is not much. And cross-attention has a higher accuracy. So if you're looking for something very high accuracy and you can use the, you have the resources, you can just plug in the cross-attention fusion. But this is the one that we picked for iiANET, yeah, the additive fusion. So, and also for effect of changing the multi-head size, and also the ratio of iiABlock. So iiABlock has ratio, which the default ratio is actually 1 to 6 to 1. So we played it by changing it to 2 to 4 to 2. And we have a huge drop in the parameters, yeah. And the flops here also drops, but at the cost of top 1 accuracy on area image dataset. So I think the accuracy drops a lot, almost by 6. So I think when we did so like we play around with it, and the accuracy drops, but the efficiency also increase. Like the learning parameters decrease and the flops also decrease. So here iiANET layer 4, and in the layer 4, because iiANET has 4 layers, okay? So in the last layer, we try to increase the head size of the head size of the multi-head self-attention, and this is what we got. And the flops increase, and the number of parameters also increase, and not much of the top one accuracy actually even dropped a little bit, but not much, So we actually added registers to our multi-head self-attention, and one of the reasons why we added registers was to kind of like improve or enhance the interpretability of multi-head self-attention. And here you can see like adding registers, iiANET here without registers. You can see the feature maps, the gradcams, and when we added registers, it improves significantly these gradcams. So this is image as input, which is a viaduct. We had mountains, we have storage tanks, and also rivers. And these samples are kind of prevalent with long-range dependencies. So in conclusion, I would like to conclude iiANET, presenting iiANET. And I think iiANET achieves a competitive performance across several tasks, and we use several data sets, and these tasks include classification, detection, and segmentation. And I think based on the experiment that we performed, we conducted, and we actually can say the architecture captures or enhances long-range dependency modeling. So it improves the global contextual understanding of complex images. And also iiANET, we achieved efficiency, which we compared the trade-off based on coordinate, VIT, and the rest, and CVT. Ours achieves a better efficiency. And also the model is less effective. This is one of our limitations. It's less effective when the objects are mostly local. So I think it's based on the way we designed iiANET. So if it's something that you have to use it for, most of the images are local, I think it's less effective than other models. And also we have a problem of the multi-branching. So I think this, in terms of like trying to find an optimal parameter was very challenging because of the scaling were very sensitive. So this is also a problem with this design. And also the parallel branch execution may introduce latency. So if there's a way we can like make it this parallel branching, because one component sometimes has to wait for the other component to finish processing. So this kind of like introduce latency during inference. So future work, I think going beyond hybrid design. So I think it's high time like the computer vision community comes up with a new approach that is going to go beyond hybrid design, and also beyond attention. One of my reasons is because attention is very, very, it's very expensive, very wasteful. And so I would like to say thank you all for listening. My name again is Yunusa, and if you have any question, you can reach me out at my email. And currently I'm residing in China. I founded NewraLab. Thank you all for listening. Take care and bye, and see you